Good morning, students. In the last lecture, we see the crystal field theory, its assumptions, its basis, and the bonding between the metal and ligand is ionic. And now we are going to apply that theory for the different complexes with different coordination number. First, we are going to see its effect on the octahedral complex, how it will be applicable, and what is the effect on the metal d orbital. So application of CFT to octahedral, square planar and tetrahedral complexes, that is coordination number 6 and coordination number 4. First we see the octahedral complexes. In an octahedral complex, it is assumed that the metal is at the center of the octahedron and the ligands are at the 6 corners of the octahedron, which will be seen in the figure in next slide. The easy orbitals dx square minus y square and dz square, or sometimes also called d gamma orbitals, are directed along the axis, and the T2G orbitals points in between the axes x, y and z. It is follow the approach of the 6 ligands along the x, y, z, minus x, minus y and minus z direction will increase the repulsion and the energy of the dx square minus y square and dz square orbitals increases. Bathy, which points along the axis much more than the xy, dyz, dxz orbitals, which have the points in between the axes. Thus, under the influence of the octahedral ligand field, the orbitals of the metal split into two groups of the different energies. See here in the figure, at the center hollow circle indicates the central metal and the solid circles indicates the ligands. See, on the x-axis there are two ligands, on the y-axis there are two ligands, on the z-axis there are two ligands. That means the minus x, y minus y, z minus z, and at the center there is the metal atom, and thus there are the 6 corners and have the 8 faces. So it is the octahedral complex. Figure will be indicates very correctly. The differences in the energy between two sets T2G and EG is given either of the symbol delta O, O for octahedral, or 10 dq. The term 10 dq stands for 10 is equal to the number of d electrons, d stands for destabilization of d orbital, and q stands for charge on the ligand. Thus we can say 10 dq or delta O in case of the octahedral field. It is measured in terms of a parameter called dq. This quantity may be smaller, but it is always taken arbitrary as 10 dq. It shows that the easy orbitals are plus 3 by 5 delta O or plus 6 dq above the average level, and the T2G orbitals are minus 2 by 5 delta O or minus 4 dq below the average level. Strong and weak ligand field splittings. In an octahedral complex, if the value of 10 dq or delta O is large, it is called as strong field splitting, and the complex is referred as a strong field complex. If The value of 10 dq or delta O is small. It is called as a weak field splitting, and the complex is referred as weak ligand field complex, which will be shown in the figure. The magnitude of 10dq or delta O depends on three factors. First, the nature of ligand. Second, the charge on metal ion. And third, whether the metal ion is in first, second or third row of transition elements. Ligand which cause only a small degree of splitting are termed as weak ligands, and those which cause a large splitting are called strong ligands. The common ligands can be arranged in the order of their strength, and this series is called as Spectrochemical Series. It is given as Cn minus is less than NO2, H2O, C2O4, 2 minus, OH minus, F minus, Cl minus, Br minus, I minus, and thus Cn produce almost double splitting than that of the Cl minus ion. So Cn minus is a strong ligand while Cl minus or I minus is a weak ligand. See in the figure there is the splitting. At the center where there is the splitting is small, it is due to the weak field, and the splitting which is large, it is called as the strong field splitting. That is, difference between T2G and EG for 10dq is small, and where the difference between T2G and EG is the large. Distribution of electrons in the d orbitals. The d orbitals are filled in by the electrons according to the following rules. The electron will be occupy the orbital of lowest energy. Second, Hund's rule of maximum multiplicity will be followed. That is, electrons will not pair up unless all the degenerate orbitals contains one electron each. That is, they are half-filled. Third, if energy required to occupy the higher energy orbital is greater than the energy required to pair of the electron, that is pairing energy, in the lower energy orbitals. That is, if 10 dq or delta O is greater than P, the electron will be pair up in the lower energy orbital. If the energy required to occupy the higher energy orbital is less than the energy required to pair up the electron in lower energy orbital, that is 10 dq or delta O is less than P, that is pairing energy, the electron will be occupy the higher energy orbital. Let us consider the filling of T2G and EG orbitals in an octahedral complex. The D1, D2, D3 electrons will occupy the T2G orbitals. Follows the Hund's rule. This filling will be the same in the strong field and weak field complex. However, a D4 system occupy the T2G orbitals and EG orbitals will be different in strong field and weak field complex. See in the next figure we will see the distribution for the D4 electrons in strong field and weak field complex. In the strong field complex, delta O is greater than pairing, so 6th electron pairs in the T2G orbitals and gives the electron configuration of the metal as T2G4 Eg0. In the weak field complex, delta O is less than P, that is pairing energy, shows the fourth electron occupies the Eg orbital and gives the electron configuration of the metal as T2G3 Eg1. Similar arrangement can be made about the occupancy of T2G and Eg for D5 to D10 system of the electrons in the strong field and weak field complex. See, here we have the example for D4 system. In the first figure, see there are all 4 orbitals in T2G orbitals. One will be get paired and 2 are unpaired. In second, there are the 3 unpaired electrons in T2G and fourth electron will be enter into the Eg, which is unpaired. So here there are 4 unpaired electrons. See the distribution of the electrons in T2G and Eg sets in strong field and in weak field. See here D1 system, D2 system and D3 system. There is the similar arrangement. For the D4 system, due to the weak field, it will be get paired and there are 2 electrons. For the D5 system, again there are the 2 pairs and 1 single electron. In D6 system, all 3 T2G orbitals will be get paired. There is no any unpaired electron. In D7 system, again 6 electrons will be in the T2G orbital, that is 3 orbitals are paired electrons and 1 single electron in Eg orbital. In D8 system, again there is the paired and fulfilled T2G sets and Eg set have the 2 electrons. Then D9, again D9, next electrons will be paired into the Eg orbitals and Eg orbital having only unpaired electron. And in D10 system, all 5 orbitals have the paired electrons. There is no any unpaired electrons. Here there is the n number of unpaired electrons and their spin, that is the S is equal to n by 2. It is also given in the table. Here we are going to see the distribution of d orbitals in T2G and Eg sets in weak octahedral field. See in the weak octahedral field up to the D3 system fulfilling is as usual. For the D4 system, electron will be not get paired but it enter into the Eg orbitals. For the D5 system also next electron will be enter into the Eg orbitals. And in D6 system in weak field it will be get paired into the T2G orbitals. D7 system next electron will be enter into the T2G, it will be get paired. D8 system again it will be get paired. D9 system, then again it will be get enter into the Eg orbitals and get paired. And D10 system again it enter into the Eg sets and it will be get paired. For the D10 system there is no any unpaired electron. Thus we see in the strong field and weak field how the electrons will be enter into the T2G and Eg sets of the d orbital. Their number of unpaired electrons and their spin is calculated here. Crystal field stabilization energy of octahedral complexes. The total decrease in energy caused by the splitting of d orbital and their occupancy by the electrons is called crystal field stabilization energy, CFSE. In case there is a pairing energy involved, it is added to the CFSE. Pairing energy is always the energy absorbed when 2 electrons neutralize their spins. CFSE is given by the formula CFSE is equal to minus 4 dq into number of electrons in T2G orbitals plus 6 dq into number of electrons in Eg orbitals. CFAC for D1, D2, D3, D8, D9 and D10 systems are the same. CFAC for the strong field and weak field, it is same for these systems. For D10 system, 5 electrons get paired, create a spherical field around the metal ion and the net CFAC is 0. The term pairing energy is not added to CFAC. The CFAC for D4, D5, D6 and D7 system in strong field and weak field octahedral complexes are different. They can be calculated as D1, D2, D3, D8, D9 and D10. Electronic configuration is same for strong field as well as the weak field, and that's why their CFAC is the same for that systems. Here we calculated for the D4 system minus 4 dq, D2 system minus 8 dq, D3 system minus 12 dq, D8 system minus 12 dq plus 3 pairing, D9 minus 6 dq plus 4 pairing and D10 0. There are the 5 pairing, but it is not calculated here, not considered here. In strong field for D4 system C, all electrons are into the D4. It is the T2G4 configuration and therefore it is minus 4 into 4 plus 1 pairing. D5 system minus 4 dq into 5 plus 2 pairing is equal to minus 20 dq plus 2 pairing. D6 system C minus 4 dq into 6 is equal to minus 24 dq plus 3 pairing energy. For D7 system also there is the T2G6 is E1, so minus 4 dq into 6 plus 6 dq into 1 is equal to minus 18 dq plus 3 pairing energy. And for the weak field system, weak field complexes, D4 system, electron configuration is T2G3 is E1, CFAC is minus 6 dq. D5 system, T2G3 is E2, CFAC is 0. For D6 system, minus 4 plus 1 pairing, and for the D7 system, T2G5 is 2, that means minus 4 dq into 5 plus 6 into 2 is, and plus 2 pairings, so minus 8 dq plus 2 pairing. This will be explained as in the shown in the above figure, and we are having the particularly CFAC for the particular ions in strong field as well as in weak field complexes.